So this video discusses about the applications of the scalar triple products, and basically in the volume of the Parallelepiped, and also that of the Coplanar vectors. So mind you, one of the properties of the dot product of the vectors is about the scalar triple products of the vectors. Now, let's say we have three vectors. Let's say we have vector A, that is given as, let's say, 2i plus 2j minus, let's say, 2k. And we have another vector, let's say vector B, that is given as, let's say, 3i and plus 2j minus, let's say, 6k. And we have, let's say, another vector, let's say, given as a vector C, that is given as 2i and plus j plus k. Let's say that is the case. So according to the principle behind the scalar product, I should say the scalar triple products of the vectors, it is states that a vector A dot times the cross product of the two vectors. You know, it is the same as, we can also have this, it was also the same as, by the way, this is what you call the scalar triple products of the vectors, where at the end of the day we obtain the scalar value. And having this case, this is also the same as having, let's say, a vector B dot, a vector A cross a vector can be a C. And also this is the same as having a vector C dot a vector B cross, let's say, a vector A. It is the same as this. So whatever the orientation we talk about, but that's how we should have to understand about the scalar triple products of the vectors. So let's have this. Let's calculate the scalar triple products of the vectors in this case. Vector A dot, a vector B cross, let's say, a vector C. Now how should we have to obtain this? So first thing, we should have the cross product of those two vectors, a vector B as the vector C. So what is the principle behind the cross product of the two vectors? So in this case, we'll have, we'll have vector B cross a vector C. That will be equal to, now we should have the cross product of the two vectors. And I understand how to operate the cross product of the two vectors. That is I, this is j, and this is k. That is, we have now for vector B we have 3, and we have 2, negative 6. In the vector C we have 2, 1, 1 in that way. So we can have it in that case. Then I'll have, a vector I, that actually a component I that will be given as 2 down 1, and that should be negative 6 down 1. We'll have that. Then minus, j will have, 3 down 2, negative 6 down 1. And plus, then we'll have k. That should be k. Now we'll have a component k that will be given as, now have a 3 down 2 and a 2 down positive 1. We'll have that. And from there we're going to have is that so now from there we'll have it as, I, and the times 2 times 1, that is 2. So 2 times 1, we have it as 2, and minus 1 times negative 6, we have it as a positive 6. So have 2 plus 6, that will be given as 8. That will be that, minus, j, and then 3 times 1, that is given as 6. That should be 3. Then 2 times negative 6, that is negative 12. And 6, actually 3 minus 6, that 3 minus 12, that will be given as 15. We'll have it as a positive 15. and plus k, that will be given as, now have 3 times 1, that is 3, minus 2 times 2, that will be given as, negative 1. We'll have that. So now have 8i and minus 15j, and plus, in this case we'll have negative k. So this is the cross product of the two vectors, as we should have to get it up. So what will go up next? Then we'll have the dot product. Then we'll have the dot product between vector A and also this other vector. So in this case we'll have 2 times 8, that will be given as 16, and 2 times negative 15 we'll have it as negative 30, and that of negative 2 times negative 1 we'll have it as a positive 2. So in this case we'll have it as, what is negative 16 should be 16 minus 30, that is negative, should be 14, plus 2, that will be given as negative 12. So that is how you should have to understand about the scalar triple products of the vectors. So this is the solution in that case. And I also at your own time try to have the following cases. And let's say we have vector x, that is given as 2, 1, 4. And we have vector y, that is given as 0, 4, 7. And let's say we have vector w, that is being given as, I'll have it as half, 4, 8. So what is the scalar triple products of these actually vectors? So try to have those at your own time. So one of the applications of the scalar triple products is about the volume of the parallelepiped. So what is the parallelepiped? Now if we say a parallelepiped, should be a sided pipe. I should have it as, we should call it as a cornered pipe. That is what you call the parallelepiped. Let's say we have this case. We may have the structure of the parallelepiped, the way you have to understand about, let's say, a carton or a cuboid as well. Let's say we have, this is a cuboid. We should have, let's say, this is a cuboid in that case. And this one will help us to have an overview what is you have to expect about the parallelepiped. Let's say we have this case. This is the simple carton. Let's say this is a carton presenting in that case. So now, assuming that, let's say this is the cross-section surface area we may think about. Now let's say this is a continuous pipe. Let's say this is a continuous pipe going over like that. And now what we have, it's a parallelepiped. So it is a pipe or hole with sides. So it is a cornered hole or cornered, I should say it as a cornered hole, should be that, or it can be that, but this is what you call the parallelepiped. So how can we be able to find the volume of the parallelepiped if this is the case? So according to the principles behind, let's say this is the concurrent point, and from this point we should have to express the sides of, let's say we should have to express the sides of this actually a parallelepiped in terms of the vectors. And then we'll have, let's say this is a vector A. Then we'll have, let's say this is vector B, and let's say this is, I'll have it as a vector C. And of course we can also have this point as the point of interest. That's the concurrent point, of which we may have this vector in this vector and also this vector as well. And even here as well, we can have, let's say, this vector as well as this vector. And also here, this vector and this vector as well as this vector. You can also have that as well. So now, according to the principles behind, using these actually concurrent vectors, we can be able to find the volume of the parallelepiped using the scalar triple products. So now, what does it state? Let's say we have a parallelepiped with these actual sides expressed in terms of the vectors. So in this case, the volume of this parallelepiped, it is given as the magnitude of the scalar triple products of the two vectors. So that is how we have to understand about the volume of the parallelepiped. So the volume of the parallelepiped is calculated using the scalar triple products. That is to say, the magnitude of the scalar triple products, that is the volume of the parallelepiped. So which means, using the previous example, you can be able to find the volume of the parallelepiped, and which is being presented using those actually given vectors. So that is to say, if we have the scalar triple product of the vectors as a negative, we just have to go for the positive value because the volume can be negative. So we'll have the absolute value of the scalar triple products of those two vectors, rather of those actually three vectors. Let's say we have a vector A. Let's say we have a vector A that is being given as, let's say, I plus 2j minus, let's say, 2k. And let's say we have vector B that is being given as, let's say, 3i plus 2j minus, let's say, k. And we have, let's say, vector C that is being given as, let's say, 3i plus j plus k. Let's say that is the case. Now find the volume of the parallelepiped with the following vectors. Now, how should we have that one? So understand that the volume of the parallelepiped, it is given as, the scalar triple products of the two vectors. So try to have this and calculate the volume of the actually a parallelepiped in that case. So if the scalar triple products will be negative, we'll have the absolute value of that one. That will be given as the positive. Let's say if we have the scalar triple products as a negative 8, so which means the volume will be given as the absolute value of negative 8. That will be given as 8. This will be the volume. So try to have that one. And finally, let's look at what we call the Coplanar vectors. So what are the Coplanar vectors? If we say Coplanar vectors, these are the vectors that are on the same plane. Let's say we have, this is a sample plane. Let's say we have, this is the sample plane as well. We should have. Let's say this is the sample plane we may think of having. And now on the plane, let's say we have, this is, I'd say, vector A, and let's say this is, I'd say, vector B, and let's say we have, this is, let's say, vector C. Now, despite that these vectors are going in different directions, but much as they are on the same plane, lying parallel to the plane of the, actually lying parallel to the surface of the plane, then these vectors are said to be the Coplanar vectors. So if now the vectors that are said to be coplanar, it means the vectors are said to be coplanar, that is if they are on the same actually plane. So how can we be able to determine whether the vectors are coplanar or not? So we use the scalar triple products of the vectors. Now in this case, if we have, let's say, 3 vectors that are claimed to be the coplanar vectors, then what it means is that we use scalar triple products of the vectors. And that is to say, if we have, let's say we have a dot product, I should say a vector A. Now I should say, if we have three vectors that are claimed to be the Coplanar vectors, now in order to verify that, then we should have to operate the scalar triple products of those three vectors, in the sense that vector A dot vector B cross vector C. Now if the scalar triple products of the vectors is given as, let's say, is given as 0, it means those vectors are coplanar. So vectors are said to be coplanar if the scalar triple products of the vectors is given as 0. That is how you should have to understand about the coplanar vectors. Let's say we have this case. Let's say we have the following vectors. Let's say we have vector A that is given as 1, 1, let's say 1. And we have vector B that is being given as, let's say, 0, 1, let's say 2. We have vector C that is being given as, let's say, 1, 0, 0. So determine if these vectors are coplanar vectors or not at your own time. Now the vectors are said to be coplanar if the scalar triple products of the vectors is given as 0. Now let's have an interest about this. Let's say Strumo, this is a plane. Let's say we have, this is a plane we can have. Let me have it this way. Let's say this is the plane. And let's say we have, points, point A, point B. Let's say this is a point C. And we have their respective coordinates in that case. So now, without having this typical, let's say, a diagram to show that the points are on the same plane or not, how can we be able to determine if these points are really lying on the same plane or not, using the principle of the coplanar vectors? How should we have to determine if these points are really lying on the same plane or actually not? So try to have how we can have it in that way. Thank you.